Good evening, students. Today's class will be taken by Prajakta Madam for 1.5 hour, that is 7 to 8:30 p.m. Madam, please continue class. Thank you.
Yeah. So in yesterday's class, we basically looked at some examples based on simple pendulum, and then we saw what is damped oscillations. First, we also looked at the angular SHM, basically, which is like a rotating disc, which is this case, and then it was a magnet which is kept in a uniform magnetic field, and what kind of forces or what kind of torque acts on such systems, and then what is the differential equation for SHM, like this angular SHM, and what is the frequency or what is the time period of this kind of SHM. And then we saw what is damped oscillations, and we then discussed this plot basically, which is of the displacement with respect to time, and this exponential curve, which is amplitude as a function of time. And we then saw what are the two major consequences that happen in a system because of damping. So first will be our first consequence of damping is that amplitude will be now a function of time, which was earlier not the case. Earlier amplitude was just a constant number, but because of damping now amplitude will become a function of time, and it will exponentially decay with time. And this was the amplitude versus time graph. And the next second consequence of damping will be that frequency of oscillations will be less than will be less when there is damping with respect to when there is no damping. And we roughly saw what the plots of these things look like. And there was like one small part of this chapter that we could not complete yesterday, which was free oscillations, forced oscillations, and then condition of resonance. So we'll quickly go through that today. So what is free oscillations? First of all the things that we have been seeing so far in this chapter, all the spring block problem or simple pendulum problem or angular SHM, these are all essentially free oscillations. So the formal definition of free oscillations is given here, which is that if an object is allowed to oscillate or vibrate at its own, without any external motivation or without any external continuous force. The object is oscillating at its own, by its own, by some internal energy. It does so with its natural frequency. So there's a concept of natural frequency, which is in case of pendulum, for example, the natural frequency, as we had seen earlier, is 1 upon 2 pi root of g upon L. So this is the natural frequency of pendulum. If it's allowed to move by its own, like we just give the initial push to the system. We take the blob of the system and then we take it here and then we leave it from here. So it is the initial motion that we are generating in the body, but after that there is no continuous force that is acting on continuous external force, of course, that is acting on such a system. And so when it oscillates with its natural frequency, which in case of simple pendulum is this value. So when an object is allowed to oscillate or vibrate on its own, it does so with natural frequency or with one of its natural frequency. So we might not want to go into this thing now, but it essentially means that there are some systems for which it has multiple natural frequencies, and you might have already encountered this case of harmonics, octaves, like that. And people who have studied music, they also know key instruments have different natural frequencies, but that's not important. But yeah, and then the example is if the bob of simple pendulum is just displaced and then released, it will oscillate only with its natural frequency. So this is the natural frequency of blocks, and such an oscillation or such a motion is called as free oscillation because there is no continuous external driving force to such a system. Now, what is forced oscillation? So, however, by applying a periodic force, the same pendulum can be made to oscillate with a different frequency. So, for example, this is your pendulum support. So, this is where your pendulum is hung, and it is doing some motion. But now, if you let's say if you put a motor here and if you add a continuous oscillatory force on this support itself, like imagine कि ये जो support है that is not rigid anymore, so that support itself is performing some kind of motion, and now because this support itself is doing some motion, that that motion might also get transferred to the pendulum, and then the kind of oscillations or the kind of motion that this pendulum will now perform will be different from its free motion, and this might lead to pendulum having a different frequency or different time period, and such a motion will be then called a forced oscillation, or the force that is acting on this support, the external force, that is often called as driver force or driving force, because it is now driving the motion. So this is the difference between free and forced oscillations. So now they have given, or like we will study one example. Sorry. Yeah. So now they like we are given one example, which is a case of ki they imagine this is like a wall, two walls, and we are standing between two walls. और ये जो wall है उसके बीच में we have put some thread or like a string, and on this string we have attached some pendula of different lengths. Let's say this is pendulum A. I mean, this is the same diagram that I'm drawing here. Pendulum B, pendulum C, and pendulum D. So if you see now, pendulum A and pendulum C have the same length. Pendulum C ka jo length hai, that is, sorry, pendulum. Okay, let's just stick to that diagram, because otherwise it will be confusing. Because I have given the names wrongly. But anyway, yeah. So imagine that these three pendulums, B, C, and D, these three pendulums are not, I mean, none of this is in motion right now, but the only pendulum that we are going to move is this pendulum A. So this is a driver pendulum, because this will now give a driving force to this entire system. So now imagine that this entire string and all the pendula that are on the string, they are moving as a single system, as one system. And what we'll do now is we'll take this pendulum and we will displace it in a perpendicular direction, basically out of the plane of the paper. So this is the pendulum, then we will take it outside in the z direction, in the third dimension essentially, and which is perpendicular to the length of this string. And now we will displace this pendulum in a z axis, and then we will leave it to oscillate in a perpendicular direction. Mind you that these B, C, and D pendula are not, we have not given them any kind of motion. So they are supposed to be stationary at the beginning. Now, as the time passes on, what you will notice is that because of the energy that this pendulum A is providing to the string, that energy is getting transferred over here, and all three of these pendula will start their motion with respect to like pendulum A, because of the energy that pendulum A is giving. And so this is the kind of driving force that we are talking about, कि हमने B, C और D pendula को कोई कुछ भी force नहीं दिया हुआ external. We have not even displaced them, and still they have started their motion on their own in the plane again, which is perpendicular to the plane of this paper. And so this is the result of forced oscillations, or the oscillations that pendulum B, C, and D are ongoing. They will be called as forced oscillations, not free oscillations. And the pendulum A will undergo free oscillations, whereas these three will undergo forced oscillations with the driving force which is provided by this pendulum commotion. So that is what they have given here, that due to transfer of vibrational energy through the string, so the vibrational energy that will be provided by pendulum A, that will go first to the string, and then from the string it will go to individual pendula. And because of that, firstly the oscillations of A will be free oscillations, and the oscillations of B, C, and D will be forced oscillations. And now if you and they will be of the same frequency as the frequency of pendulum A, so they will all move with the same time period or with same frequency. Now we will see ki what is the like what is difference, like why we have shown these three pendula with three different lengths. So first of all, if you notice, the length of pendulum A and length of pendulum C are same. So pendulum A and pendulum C, they have same lengths. What does that mean for the time period? So time period is 2 pi into root of L upon G, right? So the time period of pendulum A is just going to be equal to time period of pendulum C. That will not be the case for B and C. So the frequency of B will be, because the length is shorter, so the frequency will be higher, and because the length is higher for D, frequency will be shorter. So the frequencies of B, C, and D, within them, the frequency of pendulum A will be equal to frequency of pendulum C, and B and D will have different frequencies, some different values of frequencies. Now these we are talking about natural frequencies. So natural frequencies of A and C are same. So as a result of this thing, ki A, which is a driving pendulum, and C, which is getting driven by some other pendulum, they have same frequencies. So now what will happen is the case of resonance. Ki because these two bodies are, they have same natural frequencies, and one body is driving the other body. Because of that, um, uh, the amplitude of this motion, if you see, so as I mentioned, the frequency of all three motions is same, B, C, and D, but the amplitude of their motion will now change because of the amount of the vibrating energy that is being given to these three pendula are different. And the pendulum which has the same length and which has the same natural frequency will be in resonant conditions or in resonance condition with the pendulum A, which is the driving force. um, so so because as a result of that, what will happen is pendulum C will now oscillate with the maximum amplitude, and the other two pendula will vibrate with amplitude which is lesser than pendulum C. So within B, C, and D, the maximum amplitude will be of pendulum C, which has same natural frequency as the pendulum A. So there might be a question where you will be given like some number of pendula, and one of them will be the driving pendulum, and then you might be asked to rank the amplitude of the three pendula in decreasing or increasing order, like that. So you have to keep in mind that the pendulum C in this case, which has same natural frequency as the driving pendulum, will have the maximum amplitude of motion when they are getting driven by this pendulum. Okay, and that will be the condition of resonance. So what is the formal definition is also given here. So what they say is, it shows that the object C having the same natural frequency as that of the source. So source in this case is this, the pendulum A, because it is the source of energy or it is the driving force. So like they are equivalent terms. So the object C having same natural frequency as that of the source absorbs maximum energy from the source, and in such cases it is said to be in resonance with the source. So I hope that point is clear to you guys. Um, and the next statement is for B and C's, which is B and D pendula, which is key for unequal natural frequencies on either side, higher or lower natural frequencies, the energy absorbed and hence the amplitude. So if you remember, total energy is always Ka square. So energy and amplitude are directly proportional to each other. So if the energy of pendulum is high, that means its amplitude is high, or vice versa. So if the frequencies of natural frequencies of the other two pendulum which are not equal to the driving pendulum, they will absorb lesser energy and hence they will have lesser amplitude than the C pendulum. So this is a plot of the force frequency. Force frequency as in this is equal to natural frequency of A. So this is the forced frequency. Okay. And this is the resonant frequency, which means ki at this position where the natural frequency of the pendula that are moving, if it is equal to the natural frequency of the source, then this is this position ki F is equal to Fr of the resonance source, and Fr is the resonance frequency, ki at what position the amplitude of the pendula that are getting driven by this force is the maximum. So this is the curve for that relation. you will see that there's a maximum peak on at a frequency which is equal to the natural frequency of the source, and there you see the maximum amplitude. And for either sides, for lower or higher case, the amplitude is lesser. And I mean, I can just show you a video example. So this is the pendulum systems. Just a minute. Yeah, so this is the front view basically. So let's see ki this is your pendulum A, and this is the pendulum A and C. So they're not exactly equal in length, but they're like almost equal, so you can assume that. And then now we can see what happens if you give energy to one pendulum. So they're moving in pendulum which is black in color, which has the same length as this particular pendulum. And now you see what is happening. All the three pendula, all the four other pendula, they have also started getting in motion slowly. And now you can see which pendulum has the maximum amplitude essentially. And now they are trying to move the other pendulum. And now you will see all of the pendula have very less amplitude, which is because no other pendulum in this system has same length as the one that is getting that is oscillating essentially. In the earlier case, what was the case? कि we are moving this black pendulum, जिसका height is similar to this one, the one that is moving with the higher amplitude. So their lengths are essentially almost equal. So they are also they are moving in similar kind of amplitude. But the next case where he moves this longer pendulum, you will see that because there is no other pendulum which has same length as this longer pendulum. So all of them are now moving in lesser amplitude, moving with lesser amplitude. So I hope like that video help. I'll also put the um, link of the video in the notes. And I think with that, like we have completed this chapter. There are questions at the bottom of the chapter, and I think you can take a look at these questions and try to solve some of them. They are like good numerical examples, and there are also like some theoretical questions. You probably don't need to do theoretical questions. You can try to solve examples for now. And then we'll do a recap quickly of, because this chapter is complete now, and before moving to the next chapter, um, we'll just do a small recap of what kind of things we saw in the chapter. So basically, firstly we saw just a minute. Yeah, we first saw a spring and mass system. Which is basically a blob of or like a block of mass attached to a spring with spring constant k. The mass of the block is m, and we saw this relation, which is just F is equal to minus kx. And from there we went on to find out firstly the differential equation of SHM, of linear SHM, which is this equation. And from the differential equation we could also find the acceleration, then velocity, and then displacement in SHM. And we saw some examples based on this where they'll give you let's say two of these values. So acceleration and velocity at particular point is given, and then you have to find that displacement, or velocity and displacement is given, and you will find accelerations. In some questions like this we found in some of the competitive exams. Then third was, then we found out the frequency or time period of motion, and there were also many examples which were based on these formulae. Actually many examples, so you can remember some of these formulae. And then velocity, displacement we covered. We looked at where the values of velocity and displacement, acceleration will be maximum. So what are the boundary conditions essentially, what are the edge cases. Then the fourth thing we saw was springs in series and springs in parallel. There were also examples based on there are also examples based on these systems where they'll give you these kinds of things. So these are in parallel first, and then there is a series spring attached, and this is our block. So like what is the extension or what is the equivalent spring constant? So questions like this we saw. Then we looked at SHM as a projection of UCM. So which was this diagram, this particular thing where we saw a circle which is performing a uniform circular motion, and then we saw the shadow of that ball on a straight line, and then we figured out some formulae for velocity, acceleration, and displacement. And then these give you like the sine and cos terms, or like the sine and cos representations essentially, and then from there you can find out multiple things. um, and we saw like what is the phase difference between velocity and displacement and these kinds of things, and there was like one question which was directly based on this part, which was also asked. Then we saw superposition of two SHMs with same path. So this is also like you also saw some questions based on this part, which is like directly just two simple formulae, which is like what happens to a particle when it is imposed with like two different SHMs. And then we came to the energy of particle in SHM, and they were again like this was one of the important parts, and we saw many questions based on energy of particle in SHM. And then we did the similar thing that we had done for the spring block system. So from spring block system, we went to simple pendulum, and we again just found out the what is the relation between force and displacement. So we found out that relation, and then from there we again did the differential equation. From differential equation we could find out the frequency of oscillation, or like the time period, and based on this time period value there was the most number of questions that were asked based on the time period of simple pendulum. And then we also looked at energy. So this formula I didn't write there, but if you remember yesterday's class, then we looked at how to find the how to use the MV square max by doing the like by taking the K plus P at some random position. So that formula we saw yesterday. Um, so we also saw some questions based on that. And then there was a small chapter of angular SHM, which was not really explained much, but you might also not get many questions on that. And then there was a damped SHM, and then we ended with the resonance conditions or like driven oscillations essentially. Um, so this was all that we saw in this chapter, and I don't have any questions for today because we have almost covered all the chapters, and there I didn't find many questions on like damping and resonance conditions. So I didn't put any questions for now for today. We will now directly move to next chapter. Yeah. Uh, so the next chapter, chapter number 6, is superposition of waves. So we are still looking at waves now, but now we'll explore like superposition, which is essentially like addition of two waves, but it will be like a vector addition because waves can be looked at as vectors, because like there's a plus thing and there's a minus thing, there's a plus thing and there's a minus thing. So if two waves overlap on top of each other, what will be the resultant wave? So this is something that we will look at, we will look into in this chapter, and there are also other things like reflection and everything. um, so let's just start with the first definition, which is of the mechanical wave. So there are essentially like two major types of waves that we can like all kinds of wave that we see basically they can be divided into two types. And first will be mechanical waves, and second will be electromagnetic waves. And there are also matter waves which don't fall technically into either of these categories, but they come only in like minute scales. So we don't really see the matter waves. So the waves that we see with our eyes, naked eyes, they can be classified into mechanical waves and electromagnetic waves. So mechanical waves is essentially any wave that propagates through a medium, and when that wave is propagating, the particles of that medium will perform some oscillatory motion or some periodic motion. Whereas on the other hand, electromagnetic waves, you as you might already know, electromagnetic waves. So this is with medium, and then this requires no medium. So we don't require. I mean, electromagnetic waves don't require a medium for propagation. So without medium also they can propagate. So the formal definition of mechanical wave is essentially it is a disturbance produced in a elastic medium due to periodic vibration of particles of the medium about their respective mean positions. So elastic medium is anything, anything that has a property of like upon displacement. For example, this particle is displaced at this position now. Elastic medium will have capacity to bring that particle down to its original position. So when you take this particle and move it at different position, it can perform this kind of oscillation. So that is an elastic medium for the purpose of this chapter. So what is this? It is a disturbance produced in elastic medium due to periodic vibration of particles about their mean position. So this is some medium and it has some particle, and this particle is doing this periodic SHM motion. And because of this motion, the wave that propagates forward is essentially mechanical waves. Okay. Right. So in this process, energy and momentum are transferred from one particle to another. Thus, wave carries or transfers energy from one point to another, but there is no transfer of matter or particles of medium. So what they are basically saying is when this kind of wave propagates matlab just goes in front in some direction. So when this kind of wave propagates, it takes energy from one point to other point. So the energy is getting propagated, but it does not take this particle to this position. So the particle that is here, it will stay here only. It will not go there. It will just stay here and it will do this kind of oscillatory motion. So that particle is staying there. So it does not move the matter. It does not take the matter with it, but it just takes the energy with it. And with that energy, the wave propagates forward. Uh, and then they also talked about like there's another kind of wave, which is electromagnetic wave, which does not require material medium, and they are non-mechanical waves. So mechanical का क्या मतलब है कि when you say, for example, a mechanical clock, or you might have heard this like terminology somewhere, कि I have a mechanical clock. What that means is um, there is no electric component to it. Mechanical is basically like a physical motion of something. So when the needle in the clock turns in a physical sense, like the actual needle is moving because of some mechanical thing that is happening. Or like here, for example, the particles of the medium are moving in a physical sense. So that is mechanical. Whereas in the electromagnetic, this thing, there are no particles that are moving up and down. So because of that, it is not a mechanical wave. And then in this chapter, what we will see essentially, we'll study mechanical waves and we'll look at their reflection, the principle of superposition, and formation of stationary waves and beats. So this is just some names. We'll look into what they are now. So now the next thing, next definition or like a formal thing is progressive waves. So they are given an example of waves that are formed on the water. कि हमने अगर water में कुछ तो ऐसे stone वगैरह ऐसे drop कर दिया तो you have seen कि there are like ripples of water that just go around, right? And so what you will see essentially is कि these ripples are moving forward, like they look like they are moving forward. कि यहाँ का जो like this top part now will go आगे, and then you will see a flat part here, and then you will see a negative thing here. So like that, the wave is moving forward. Like it looks like the wave is moving forward, and so that is essentially a progressive wave. Progressive wave money, it is going in some direction. It is moving forward in some direction. So the disturbance slowly speeds, and distant particles get disturbed from their position at rest. कि you have seen this कि आपने पत्थर यहाँ पे डाल दिया, so this is the position where you have thrown the पत्थर, and suddenly the moment you put the stone, you will see some wave that is that has started from here, and the rest of the water is still is like it's not moving. Then eventually this disturbance will travel forward. So this particles will start moving, then this particles will start moving, then these particles will start moving. Slowly the wave propagates in some direction, and then जो दूर के particles है, दूर के particles है, they also start feeling that vibration. So that is how the energy is getting transferred. कि पहले यहाँ पे कोई wave नहीं थी, पर the moment you put the stone in here, धीरे धीरे that wave traveled and it reached this point. So because of that, we'll call it a progressive wave. कि slowly the energy is spreading in some direction. So the formal definition is a wave in which the disturbance produced in the medium travels in a given direction continuously without any damping or obstruction from one particle to another is a progressive wave, or similarly it will be called as traveling wave. So traveling is a simple, matlab, it is the same meaning in like normal English. Ki the wave is traveling essentially. The energy that the wave is carrying, that is also traveling with it. So that will be a progressive wave or a traveling wave. So they have given like examples ki sound wave jo hai usme the pressure waves, the compressions and rarefactions, they travel along the direction of propagation. We will see this like in the further page. And now the important thing is properties of these. I'll just erase this. So you look at properties of progressive waves. So first property is each particle in a medium executes same type of vibration. Particles vibrate about their mean positions, performing simple harmonic motion. So this is what I also explained previously, which is key. Like when a wave is passing over, say, this particle or this particle or this particle, this particle, these are all particles of medium. What is happening is this particle is first going up, then it is coming to the mean position, then it is going down, then it is again going to the mean position, and like that this is performing a SHM. This is a simple harmonic motion. So all of these particles, they are all performing same kind of SHM. They are performing SHM first of all. So particles perform SHM, but they also perform same kind of SHM, same type of simple harmonic motion. So they'll all at some point they'll all be at mean. They will, like, some of them will be at mean position, then some others will be at the highest, like, or the extreme position, or some will be at the negative extreme position. But the motion of them is all of them is similar kind of. Then the second thing is all vibrating particles of the medium have same amplitude, same period, and same frequency. So the amplitude A, period T, and frequency F or omega, they are all same for different particles. So this is also equivalent to saying that they are performing similar type of SHM because their amplitude and period are same. Then the next is the phase. That is the change, state of vibration of particle. It changes from one particle to another. What this means is कि let's say कि हमारी wave ऐसे propagate कर रही है. It is some transverse wave, and this is the mean position. So this is my particle at moment t is equal to 0. Okay, so this particle now has come here. So this was the mean position of the particle, but at t is equal to 0, this particle is here. Because the wave has to propagate like this, so particle has to come here. Now let's say at t is equal to some time t1, the wave has now moved forward, and now the wave looks like this. So now the wave has moved forward. This lower bottom has moved to here, and this upper point has moved to here, and now we have this point here. And now this same particle, which was here earlier, which was earlier here, now it has moved to this position. So similarly, if you look at this time t is equal to 0 itself, then this particle, the particle जिसका mean position ये है, that particle is right now here. Whereas the particle जिसका mean position ये था, that particle is now here, right? So what this means is कि ये जो particles है, दो particles, उनका amplitude वगैरह सब same है, पर इनका phase change हो गया है, क्योंकि they are at different positions now. They are at like pi by 4 difference from, no, pi by 2 difference from each other. So this difference is pi by 2, right? Pi by 2 radian. So they are pi by 2 radians away from each other. So their phase difference, so delta phi is going to be pi by 2, like that. So that essentially means ki their phase is going to be different. So these all three quantities are same, but phase is different for different particles. Then fourth point is no particle remains permanently at rest. Each particle comes to rest momentarily while its extreme position, while it is at the extreme position of vibration. And then the next is the particle attains maximum velocity when they pass through their mean positions. So this is something we have already seen in the SHM. What this is essentially saying is ki every particle comes to rest while it is at the extreme position of vibrations. So what this is saying is essentially V at extreme position is equal to 0. And what the next thing is saying, the particles attain maximum velocity when they pass through their mean positions. What that means is V mean is equal to V max. So these are the relations we have already seen in the earlier chapter for a linear SHM, for any kind of SHM essentially, कि जब particle extreme position पे होता है, जब पार्टिकल एक्सट्रीम पोजीशन पे है तब उसकी वेलोसिटी इज इक्वल टू 0, और जब पार्टिकल मीन पोजीशन पे आएगा तब उसकी वेलोसिटी होगी v is equal to v max. So this is something you probably already remember from last chapter. That is essentially the same thing that it's saying. Then the next thing is during the propagation of wave, energy is transferred along the wave and there is no transfer of matter. This is what I already said कि SHM में energy is getting transferred. Energy transfer, yes, but matter transfer, no. So the matter is not getting transferred. So this particle is not going anywhere. So this particle is staying here only, but it is just doing this upward, like this up and like to and fro motion, oscillatory motion. So there is no transfer of matter, but the only transfer happening is of energy. Now the seventh point is, oh, this was 6. Third point is the wave propagates through medium with a certain velocity. This velocity depends upon the properties of medium. So we will see this. You might have already seen if you have learned the refraction of light or refraction of light basically. Then you have already seen that velocity of uh, the motion of the wave, basically velocity of the wave essentially, that is dependent on the properties of matter. And we will see this in detail further. So for now, you can just remember that the velocity of the wave is dependent on the properties of matter. It has a specific velocity, first of all, and then that velocity is dependent on the properties of matter. So the wave will not propagate with same velocity in two different media. लाइट का भी आपने अगर स्पीड देखा तो एयर में जो स्पीड है लाइट का, दैट इज डिफरेंट फ्रॉम, आई मीन ऑफ कोर्स वी आर टॉकिंग अबाउट मैकेनिकल वेव्स हियर, बट लेट्स से साउंड का स्पीड, साउंड इज अ मैकेनिकल वेव. सो द स्पीड ऑफ साउंड in air or the speed of sound in let's say liquid is not the same. So that is the difference. It depends on the properties of matter. Then the eighth thing is progressive waves are of two types: transverse waves and longitudinal waves. So we'll just make a difference table kind of thing. Transverse waves and longitudinal waves. Right. So first thing I can just draw both of them. So we'll just draw a transverse wave. So this is just the amplitude. Then this is lambda. And we'll see what else we can show. And the longitudinal wave will draw in form of compressions and rarefactions. So we can just say These are like compressions, and these are rarefactions. Again compressions, again rarefactions. So this is a form of longitudinal waves. And based on this, we'll look at the differences. Sorry, we'll look at the properties of either of them. So firstly, a transverse wave vibrate. So in a transverse wave, vibrations of particles are perpendicular to the direction of propagation of wave. So the direction of propagation of wave is always this. We will assume that the wave is propagating in x, like positive x direction. And the vibrations, direction of vibration, so these are vibrations, right? So what this is essentially saying is ki vibrations of particles are perpendicular to the direction of motion. So the wave is going in this direction, but the vibrations are in perpendicular direction like this. So second difference will be vibrations perpendicular to propagation of wave. And similarly, here the counterpoint here will be vibrations are parallel to the propagation direction, right? The wave is moving in this direction only, and the particles are moving. So here there's like a rarefaction, and then there's like a compression. So these are vibrations, and then again there's a rarefaction, and there are like again compressions. There is rarefaction, and there are compressions like that. So the vibrations in this case are parallel to the direction of motion. So this is first difference. Then the second difference is because of this kind of vibration, the transverse wave produces crests and troughs in the medium of travel. So this is a crest, the highest amplitude essentially, and the negative side of that is crest. So here we will have troughs. Sorry, what did I write? This will be trough. So there will be crests and there will be troughs. And simultaneously for this side, it will be in longitudinal waves, vibrations are parallel, and there are compressions and rarefactions along the direction. So these are essentially compressions because the waves are compressed, and these are rarefactions. So compressions and rarefactions. Right, and then the next important difference is both the transverse as well as the longitudinal waves. They can propagate through solids, but only longitudinal waves can propagate through fluids. So we'll write a difference here. Can propagate both in solids and fluids. So fluids matlab both gas and liquid. And here the point will be can propagate only in solids. So why transverse waves can't propagate in fluids has to do with a property of fluids, which is with a property of solids, which is elasticity. So I'll not go in the details of that. You can probably also read about it. It is an interesting question of why transverse waves cannot propagate in fluids. You can read about it as a homework probably. It's an interesting question. It has a very simple answer though. And these are the differences between the two types of mechanical waves, which are transverse waves and longitudinal waves. So, for example, longitudinal waves are like example of this is sound waves. And example of transverse wave could be like waves on string. Or like waves on waves on string. So for example, this is a wall, and to the wall you have attached this one long rope or string, and you are standing here, and you just moved your hand in such a way to give rise to this kind of like an oscillatory motion. So that is a transverse wave. You can see the crest and troughs also very clearly if you do it. uh, and then now they have given like a form of displacement of particle for a transverse wave. So or any both transverse and this thing, longitudinal waves. So when a mechanical wave passes through an elastic medium, the displacement of any particle of medium is can be given by this formula, which is like a displacement in mechanical wave, let's say, is given by y is equal to f of x minus vt. So this minus sign comes when the wave is propagating. Wave is propagating in positive x direction. So like this is your wave, and this is the time. Sorry, this is the yeah. This is, let's say, this is time, and this is your y-axis, and this wave is going in a positive direction, right? And and that is when the positive, negative sign will appear, because if you see here what they're saying, this is like a good explanation. So when yeah, so when the disturbance is produced at point x, let's see, this is point x in like a space, and this is where the disturbance is produced. So this is where the wave has originated from. At point x, at time some t, it reaches point x is equal to x naught. So at time, so this is where it produced at time t is equal to 0 at position x. Eventually, after some time, this disturbance will propagate to some point x dash at some point, some time t is equal to t dash, right? Because it is a progressive way, so it is going to move further in some direction. It reaches the point x is equal to x dash on right. So this is on the right side. Um, yeah, at time t is equal to at time t plus x divided by v, we can say that the disturbance of particle has reached here. So basically, if you remember the relation between velocity and time, so velocity is given as x divided by t, right? So let's take a simple example. Now let's forget disturbance and all everything. Let's say you are just standing here for a race. Okay, so this is where the race starts, and you have to reach this point x dash to finish the race. And now let's say this is a 0 point, this is some point 0, and you are standing here in the midway. So this distance is, let's say, x. So your displacement already, like at the beginning of the race itself, your displacement is x, and you have to reach the point x dash. Let's say your velocity is v. So how much time will you take to cover this distance? So you will have x dash minus x. This is the distance that you need to cover, right? So this is the x dash minus x distance that you need to cover, and divided by your velocity v. So this is the amount of time that you will take. And so because of this, so you are already at x position, and now you're moving in the positive direction. So if you look from your perspective, then this the displacement that you have done will be x plus v plus t, right? So v into t is the distance that you have covered in time t, and x is the original displacement. So you are already at x position, and then in addition to that, you have covered this v into t distance. So the total displacement that you will have after time t is x plus v into t. But here we have the sign minus. So why is that? Is because you are looking from the perspective of this position. So you are assuming that you have already reached this position, and then now you're looking back at where you had started from. So the wave in this case, it started from x and it reached x dash in t time, but after reaching x dash, now we are looking backwards कि अगर अभी हम यहाँ पे है तो हमने शुरुआत कहाँ से करी थी. So because हमें अगर शुरुआत का if we have to find the displacement at the beginning, then we will just reverse this sign, because we are looking from the perspective of from this position. We are looking backwards, right? From the perspective of wave, which is at position x dash already. And because of that, this negative sign will come. So this is like a way to remember कि अगर direction of propagation is positive, then the sign here x like x or vt के बीच में जो sign है, that will be negative. And if the wave is propagating in the opposite direction, in this direction, then the relation you will have is f of x plus vt, because you are always looking from the perspective of this position, from the end point, from where you have already reached. From there you are looking backwards. So because of that, the sign is getting like flipped. Like I hope that point is clear. Or you can always remember, just remember this कि जिस direction में wave propagate हो रहा है उसके opposite sign होगा x और vt के बीच में. Right. And this is like an example, this is like a generic equation for any kind of mechanical wave that is propagating, and the value of this f, मतलब कि क्या function होगा, that will depend on what is the source of your disturbance, कि क्या produce कर रहा है वो wave, उसके ऊपर depend करेगा कि exact nature क्या है. But whatever function it is, it will always be a function of x minus vt. And now we will look at like a specific example, which is कि if the source of disturbance is performing simple harmonic motion, कि जैसे you are standing here and you are giving this motion, कि you're waving your hand in a simple harmonic motion, like you have hold the string, you are holding the rope, and then your hand is performing the simple harmonic motion. So in that case, the wave that will be produced, that wave will have this kind of structure. And if you remember, already we have seen this kind of thing in SHM, which is a sine omega t plus phi. We had already seen this, and this is like a similar form of equation, but we have now some new variables. So this is like so y of xt, which is just equal to a sine kx minus omega t. Earlier, what the expression that we had was a sine omega t plus some phi, and it was like it was only function of t. So this was all only y of t is equal to a sine. This is the equation of SHM. But now we have this additional dependence of displacement. Why do we have that function now? It's because this is a traveling wave. This x, the dependence of x, the dependence on displacement, it comes because the wave now we now have a wave. We don't just have a particle. So you have to understand that difference. In both cases, the particles are performing SHM, but in the previous chapter we only saw one particle. So only this particle is staying here and doing this SHM motion, and that motion is only dependent on time. So this is the only dependent. This is the only factor that it is dependent on. But now what we are looking at, it's an ensemble of different points that are performing their individual SHMs, right? And this ensemble of points performing SHM simultaneously. So they are all performing SHMs, and this is giving rise to wave. And wave, that is particularly a traveling wave. So what that means is like this energy is getting transferred from this point to this point and this point to this point. So there is something that is moving in x direction as well. So this is the x direction. So definitely with respect to time, your thing is changing definitely, because each individual SHM is dependent on time, but it is also dependent on x, because this wave is traveling, because the energy in this wave is getting propagated from one x position to different x position. So because of that, we have this x dependent in the wave case, which was not there in a single particle performing SHM. And so this is a form of the displacement in the y direction of the wave. So you have to keep this in mind. Okay, this is only for a single particle, whereas this is for entire wave, right? So what is the displacement as a whole of as a combined motion of all particles, and that is dependent on x position, and that is also dependent on time. Now like the some of these things, I mean all of these terms we have already seen. Ki we have seen k kya hai, we know omega kya hai, and these things we have already seen, but there are now some new definitions that I'm going to introduce. um, so I'll just write this again. um, right, and then k ka k we can also define or write in terms of this, which is k is equal to just 2 pi upon lambda. We will not think about how this equation came about, but this is something you should remember. So earlier the definition was m omega square is equal to k, and then k, k was m omega square. This was our earlier definition from the last chapter, but this is now a new definition of k. The k is same. K is still the same thing, but it now can be represented in form of wavelength. So this is the wavelength of the wave. Um, and so this thing, there's a another definition here, which is 1 upon lambda factor. It is also called as wave number, and it has a unit of per meter because wavelength is in meter. So this is basically कि हर like uh, 1 meter distance में कितने number of waves आएंगे हमारे. So that is why it is inversely proportional to lambda. And then another definition we'll see here is of omega. So the next relation is v is equal to omega upon k, or simultaneously you can write omega is equal to vk. So if you simplify these, you will see ki v into, we can put this 2 pi upon lambda, and then lambda has lambda. Let's say it's just some length unit, and then we can also write this as 2 pi upon v upon r. So v upon r is essentially our regular angular velocity, but now there is a 2 pi factor here. So we'll not see where these formulae originate from. There is a reason to them, of course, but for now we will just assume that these are two new formulae that we are learning. कि k का नया definition है 2 pi upon lambda, और omega का नया definition है vk, और v is equal to omega k. And then we can just plug these here. I mean, we'll not use them right away and right now, but in the further chapter we will see these definitions again and again. So they have just defined these things now. And then this is just a relation if you want to take a wave that is going in a negative x direction. So if the wave is propagating along negative x direction, then this sign will just change. So instead of plus, you will just get minus. Instead of minus, you will just get plus. So we will come back to this equation again when we are looking at the superposition. But for now, you can just remember ki this is a new equation that we saw, and these are the new definitions that we saw. And these definitions of k and omega we will use in rest of the chapter. But before we move on to the superposition part, there is a next like topic, which is reflection of waves. Yeah. So and this is a reflection specifically of mechanical waves. So everything we will see in this chapter is related to mechanical waves. So this is not like optics. So don't think of reflection of light from mirrors and all that. We are not we'll not look at EM waves ka reflection, but this is instead mechanical waves ka reflection. So if you remember in like electromagnetic waves, if I had to like draw a parallel, then we had like two media. This is medium 1 and this is medium 2, and we had like refractive indices of these two media. So this is like N2, this is like N1, and we will say ki if N2 is greater than N1, then this is a denser medium, optically denser medium. right? So this is all in optics conditions or like optics terms. So this is optically denser medium, but we can draw similar analogy for mechanical waves as well. So for mechanical waves, we will have similar concepts of a denser and a rarer medium. And we will see how will a mechanical wave reflect from a denser medium and how will it reflect from a rarer medium. So firstly we can consider key from a denser medium. Okay, so in that first we will take an example of transverse wave. And then we will look at, yeah, then we will look at longitudinal waves. So let's just say we have like a wave which is like these are two. This is like a, let's say this is a medium boundary. So this is a medium boundary, and this is a denser medium, and this is a rarer medium. And this is where our wave is traveling from. So this is like a this is a wave which is traveling. And what will happen is because this is a denser medium, so let's say this is like a wall or something like that, like a physically denser medium, uh, and when this wave travels, the energy that each of this particle has, it will try to like the particle here will try to pull this particle down, and then neighboring particle down, and then neighboring particle down, and then particle here will try to pull the neighboring particle up and neighboring particle up, like that. This is how the wave will propagate. But when the particles reach this boundary condition, this particle, the particle which is here at boundary, it will try to pull this thing up. So let's say if a wave comes here as a crest, so this is the crest part that is here, and then this particle is trying to pull this thing up, but because this medium is a denser medium and the particle does not have enough energy to oscillate the particles of a denser medium, because this is a rarer medium, and in a rarer medium it is easier um, for particles to leave their motion and come back, whereas in a denser medium you will require a higher amount of energy, which this wave does not have. So this wave essentially does not have enough energy to pull these particles upwards, and because of that uh, these particles are not going to move upward, they will just stay like this, and they will insert an opposite force. So say let's say this wave is imparting some force on this boundary, okay, and because of that force the particles of a denser medium are not moving at all because it is not an enough energy. But on the other hand, similarly, because of Newton's third law, the particles of this denser medium are also giving some opposite force on the particles of rarer medium. So because of the third law of third Newton's third law, ki two bodies which are in contact, you will have an equal and opposite force. So how much ever force the rarer medium particles are imparting on the denser medium particles, same amount of force the denser medium particles are also imparting on rarer medium particles. And because of that, what is going to happen is the same force cannot do anything in the denser medium, but the same force can move the particles in rarer medium. And so what is going to happen is, because of this opposite force, the moment of this particle is just going to be in the downward motion because of the opposite force in the negative direction. uh, and so a wave that came as a crest is going to get reflected as a trough. So the takeaway is essentially crest will be reflected as a trough. And similarly, same thing will happen for a incident trough as well. Ki when the this when the particles in this, the same thing, I mean the same, there's no point in repeating, but the fundamental thing is same. Ki now the particles of rarer medium will try to pull down the particles from the denser medium, but that will also not work because they don't have enough energy. But the denser medium will impart some force on them, which is in the opposite direction, and that force will be able to move these particles in the opposite direction, which is in the vertical, which is in the direction of crest. And because of the same thing that will happen again, a trough will be let me just write this like properly maybe. So so for reflection from a denser medium of a transverse wave, firstly crest will be reflected as trough, and secondly a trough will be reflected as a crest. So this is when a wave is incident from a rarer medium on a denser medium. And then we can look at so this is like a visual representation of this key reflection of a wave pulse sent as a crest from rarer medium to denser medium. So you can see this came as a crest, but while going it went as a trough. Yeah. And the next case will be, so first we saw transverse wave, and then we can see also longitudinal wave. Same thing is happening. This is a rarer medium and this is the denser medium. And now these are the compressions and these are the rarefactions. And let's say a compression has hit the uh, denser medium. So this is a compression coming from rarer medium on a denser medium. The same thing is again going to happen. Ki whatever energy these compressions have, they are trying to move this denser medium. But again, because the denser medium requires higher energy to move, which these particles don't have, there'll be no effect on the denser medium particles. So the denser medium particles will do nothing. They will just stay as they are, and they will also impart the negative, equal and negative force on these particles. And so this negative force is just going to again compress this part of air, because you have some force, and this is like a rarer medium. So this, because this is a rarer medium, this force is enough to compress like this portion of the air, and there is again going to be a compression here, and there is again going to be a rarefaction here, and there is again going to be a compression here. So what that essentially mean is a compression will be reflected as a compression. And similarly, when a rarefaction hits on this thing, the rarefaction is also it will try to impart some pressure, and then nothing will happen to denser particles. But again, there is opposing force, and because of that, because now there is only small amount of force, because rarefactions are not going to impart as much force as compressions will impart, because compressions are like compressed passage of air essentially. They will impart a higher energy on this wall, and the rarefactions will impart lesser energy, and this lesser energy in equal amount will be imparted again back on the rarer medium by denser medium. And because of that, the air will not get as compressed as it was getting like in this case. So the rarefaction will stay a rarefaction, and then there will be like a compression here, and then there will be a rarefaction again here. And what that essentially means is a rarefaction will be reflected as a rarefaction. So we'll make a table after, like, once we look at all the cases. But this is that example. Yeah. So this is a no, this is a rarer medium. So this is here a reflection of longitudinal wave from a denser medium. So we have here a compression which is incident, and the reflected wave is also a compression. So compression is reflected as a compression, and the rarefaction is reflected as a rarefaction. And then the second case will be now. So first we saw reflection from denser medium of transverse wave and of longitudinal wave, and then we will now look at reflection from rarer medium. First case again will be of transverse wave. So now this time, this is the denser medium, and this is the rarer medium. And now let's say this is the direction of propagation, and this crest is now incident on the boundary. And now what is going to happen is, because this is a denser medium and these particles have higher energy, because these particles are of denser medium and they require higher energy to move. So these particles are carrying higher energy than they are carrying in the earlier case. So they will impart this higher energy on a rarer on the particles of rarer medium. And what is going to happen is, because this is a higher energy, and this is a rarer medium, so these particles will now move. So these particles will now move and they will impart a lower energy to them. So whatever the wave will pass in whatever form it wants to, but what will happen, like what is the net effect of this, is that the external force, or the equal and opposite force that is getting acted on this, is going to just keep this crest as a crest. It is not going to impart a force so big that it will turn the crest into a trough. So essentially, half of the, or like some amount of the wave is getting transferred as a crest, because the rarer particles are now, they have started to move, and because of that, whatever energy is getting back, whatever the remaining energy is, that is getting spent into the denser medium particle, and that will keep the crest as a crest, and it will now not change into a trough. So what that will mean now is, um, crest is going to be reflected as a crest, and the same thing will happen with troughs also. So the trough will get reflected as a trough. And this is like an example here, like a visual demonstration, a reflection of wave pulse sent as a crest from denser medium to rarer medium. So this is denser and this is rarer, and like the crest came from this side, and while going also it stayed as crest. And like these are just some examples that they have given, by the way. Like these things that they have given is just like try it out yourself kind of thing, and then you have to note what observations you see, and you can you should just read through these all things to see what, like what is, like how these examples are given essentially. um like this is basically they are saying ki you stand here and you make a wave on the string, and there'll be a wall first here, and then there'll be like a rarer medium. So this is like an example, or like a practical kind of thing that you can read. And so here basically we're saying ki crest is reflected as a crest, and same for troughs. And then the next thing will be reflection from rarer medium of longitudinal waves. And now again, this is a denser medium, and this is rarer medium. And then let's say compressions are incident. These are rarefactions, and these are compressions. So compressions are incident here. And again, what is going to happen is there will be a higher energy which is imparted on the particles of this side, of the rarer side. And because of this higher energy, these particles will also start moving now. And essentially what will happen is, you have to imagine this key, how, like, because these particles have also started moving, so now this compression is entirely going to transfer on this side, and these particles are now going to get compressed, and the compression will move in this direction now. And what will be remaining here, so this entire wave will shift in the forward direction. This compression will transfer into the rarer medium section, and now what will happen is we will come here now. So this part has moved here, okay, and that will be our reflected wave essentially. So because of the energy exchange and because this is a rarer medium, these particles have now started moving, and this compression has been forwarded into the rarer medium. And now what we have at the boundary is these rarefactions. And so what that means is a compression is going to get reflected as a rarefaction. And a rarefaction is going to be reflected as a compression. So this is the example, reflection of a longitudinal wave from a rarer medium. So this came as a rarefaction, but this is going back as a compression. And I mean, we can just make a table of all these conditions. So first here will be a transverse wave, and this will be longitudinal wave. And then here we have from denser medium, and this is from rarer medium. So when a transverse wave gets reflected from a denser medium, the crest will be reflected as straw and straw will be reflected as crest. So this can be just simply written as crest will be reflected as straw and straw will be reflected as crest. And for longitudinal wave reflected from a denser medium, compression will be reflected as a compression and rarefaction will be reflected as rarefaction. So we can just write compression reflected as compression and rarefaction reflected as rarefaction. And for the reflection from rarer medium, we have crest reflected as crest and straw reflected as straw. So crest reflected as crest and straw reflected as straw, and compression reflected as rarefaction and rarefaction as compression. So compression reflected as R and R reflected as C. So this is a table that you can remember, or you can always derive from this principle of how much energy is getting applied and whether it is equal or whether it is enough to move particles of rarer medium or particles of denser medium. So like that also you can like you can just derive this table on spot as well. But it's just easier to like remember, of course. And so this was the part of reflections from no reflections of um, mechanical waves. So I'll just give it a header. Yeah. And then now we'll come to next part, which is superposition of waves. We will not cover, I mean, we'll not look at the mathematical equations for this today. I'll just explain like very in a like just theoretical manner, like a very conceptual manner of what is exactly superposition. So superposition is basically if you when you let's say you're standing here somewhere and there are like multiple sounds. Let's say you're standing in a market and there's like a sound of this vehicle that is coming from this side, and there's a sound of like some announcement that's being made. Yeah, sorry. So there's like some loudspeaker here and that sound is coming to you, and there is like some someone is playing like some music, for example, on street, and that sound is coming to you. So these are all sounds that you hear every day, and you hear basically multiple sounds at the same time. And you have observed that you can still distinguish all these sounds differently, right? You can tell that this sound is coming from a car, you can tell that sound is coming from a loudspeaker or from a person. You can always tell apart these sounds. It doesn't happen that like two sounds mix in your head and something else, like something else becomes of that sound. So, and that is not an obvious thing. I mean, we take it for granted in in some sense. Like we think that is how it is supposed to be. But for example, let's say you mix two colors, and they are not going to stay the same, right? If you mix a red color and a green color, you're not going to get a color which is like they're not going to stay separate in your head. You'll see a color which is like a mix of red and green, right? But that is not something that happens with a sound. You can always tell apart different sounds from each other. And so this is a property of sound, which is essentially that, let's say this is a one sound wave that is coming from this direction, and then this is a longer wavelength sound wave, it is coming from a different direction, and you are standing here and you are experiencing both of these sound waves simultaneously. It is a property of sound that when two sound waves um, come at a same position simultaneously, they behave like the other sound wave does not exist or it is not there. And so you will hear this sound wave and this sound wave separately, as if you will hear them independently. Imagine this sound wave is not here right now, and only this sound wave is here, and you will hear like some person talking, for example. And then if this wave is not here and only this wave is here, you will probably hear some vehicle like honking at you. um, Even when both of them are acting simultaneously, even when a person is talking, when a vehicle is passing by you, you will still hear these two sound waves distinctly, separately, and like the other wave is not there. Like the other wave is like it's just not there. And so that property of sound makes it possible for us to differentiate different sounds that we hear simultaneously. And so I think this is what has been given here, which states that when two or more waves traveling through a medium pass through a common point, so this is a common point, and this is like two waves of different properties are passing through the same point. Each wave produces its own displacement at that point. So this wave is producing some displacement of this particle, right? So the particle might be here, it might be here, it might be here, it might be here. So each particle is getting displaced in a certain way because of wave number one. This is wave number one. And let's say there is another wave. Uh, there is another wave, let's say like this. No, I want to show something different. Yeah. So now this particle, for this wave, it is at the bottom. For this wave, it is at the central. So there are two different waves, and they are causing different kinds of displacement or different amounts of displacement of same particle of the medium. And each wave is producing its own displacement at that point, independent of the presence of the other wave. Like the other wave does not exist. So this particle, if it is getting, if this is a wave number one, and wave number two is, let's say, like this. So in this wave, the particle is performing this upward motion, whereas in this wave, the same particle is performing this downward motion. And the net result of this particle is going to be a vector sum of the amplitudes of both of the waves, right? Like the other wave is not, it does not exist there. And the resultant displacement at that particle is equal to the vector sum of the displacements due to individual wave at that point. So this is essentially superposition principle. When two waves or multiple waves, n number of waves are acting on the same particle at the same time, both of the waves will create some amount of displacement of that particle, which is independent of the presence of other wave, and that is the superposition principle. And the resultant amplitude or resultant motion of that particle is just going to be vector sum of the displacements given by two different waves or n number of different waves. So that is the principle of superposition. So I'll stop here. We have also like reached our time. And then we can discuss like the mathematical derivations of superposition principle in the next class. So I will update the next the notes page that I have. I'll update it on the Google Drive, and you can go through it. Santosh, are you there?
Yes, madam. I'm there.
Huh. Yeah. So we can stop like today's class.
Yes, yes. Thank you so much for taking care of 2 days and that 2 or 3 hours. Thank you again, madam. Students, today's class was again 1.5 hour, yesterday 1.5 hour. It's a big coverage of syllabus. So just do revise whatever madam is taking. And after that, also you have any doubts, you can just WhatsApp me. I will forward it to the madam. Madam,
Yeah,
thank you again.
definitely.
Good night and good
Yeah.
night, everybody. Bye bye. Take care.